side.
Huh.
Kind of limited our rotation, but it did help.
Yeah.
This one right here was a bit of a struggle at first because of where we actually had to place the robot there. This one is probably the most interesting though.
Yeah, it would totally, this was a hard one.
Oh. Oh.
Now, if only you would do that in competition.
Yeah.
Ours design frame buys parts. The frame needs to be designed around the game. You can design a frame that is really sleek and cool looking, but then you get to a part of your game that won't allow that. So instead of trying to design to make your robot look cool, it's easier to design it to make it function. And then once you get everything function, then you might be able to go through it with the students and they can kind of make things look cooler. Like our kids said, let's color coordinate. They was trying to use certain colors. And so they color coordinated it. You know, they thought they wanted to do. Let's start at my beginning. When you're designing with kids designing the frame, the judges are going to check to make sure it's durable, and mechanically efficient and mechanized. It's right off the judges list. When you're doing the durability, you want something that is not going to fall apart easily. If you put just two Lego pieces together and they come apart easily, that's not good. So you reinforce it by adding extra structure to it. And that's something the kids will need to test and work on. As they're building and designing, they need to keep track, write down or note what they're doing and what problems they're having. And keep track of all that. The judges love to hear that you have problems and you solve them as they work through it. They build a frame, build something, a drive system, and the frame and drive system works really well, but then they go to grab it and it falls apart in their hand. Well, that means it's not going to be strong enough. And the judges will check them on it. So then go back and reinforce it. The problem with over-reinforcement is it makes it heavy. When it makes it heavy, then it don't steer as well and move as well. But then you just gear it down. The more you gear it down, the slower you're going to go. The kids also need to work with that. Test the gear ratios. Test how fast it goes. See how much time you have. If you're a rookie team, do only a few missions, and then you have plenty of time to design the 3 missions. And when you're building that robot, it'll be easy to build around 3 missions as opposed to 12 missions. And they could build a real good, solid robot. They could actually gear it down. And the problem, the worry about gearing it down is it makes it slower, so you can't do all 12 missions. But if you're doing 3 or 4 as a rookie, then you don't have to worry about the time. You can make that thing rock solid. You can design it. You can do a lot of things to it that the judges will love. If you're trying to do all the missions, then you got to be really elegant with your weight and your design because you want to be functional. Most important to complete the task. But then you've got to be strong and you don't want to overweight it. As you go through it, it's a trial and error. It's always a trial. Just like any engineer process, you've got to try it, do it, try it again. You can't build it and say good enough because it usually isn't.
Yeah, good enough is when it works perfectly every single time.
Right. This is last year's game. You've seen it on the screen there. the new game you've seen out there. This gives you a physical idea of how big the table is, how everything looks. This robot actually is pretty large. This is probably the biggest robot we ever built. And there's lots of different parts to it. We've got this tier arm, which you've seen function on there. We have this part here which attaches. A lot of these parts, like this is one that we changed, which isn't on there. When we was trying to kick the item down there, it wasn't being consistent. Sometimes it would miss. So we used this to have this little tiny wheel to run along the wall to guide it all the way down. We built it out enough so as it run down the wall, it would exactly hit the right spot. So we use that wall. I've seen a lot of teams try to do these games without a table. When you put it on the floor and you don't have a table edge to follow, it really can disrupt how you can do things. You really want to use this edge as much as possible. So when you're designing your arms and your body, you can use that wall. Really, really helps. And you can use weights. You can get Lego weights. This is a Lego weight. Pass it around. It's pretty heavy. We've got a few of those. I'm not quite sure we got it. I think we got it through one of the games. Years past, I think it come with weights.
And also understand for the tables, every table will be different. So
Yes.
be cautious on utilizing too much of the table to the point where it works perfect on your practice table that you have at your place, and you go to competition, it's different. You know, a lot of people will blame the tables, they're not built right, and they're made differently, but that's just part of the game.
The mat can be adjusted up to 1/4 inch, 3/8 any direction. So that can throw you off. So if you can use light sensors to find lines or pull locations on the table, that'll help you keep square on the mat. It's like we had to go from here and hit that spot down there. Well, it kept this distance where this mat is up against this table always changed. So what we did is found this line at the edge of the home base, and when it hit that line, it was its starting point. So every time it would go the same amount. But also what's a different effect is, believe it or not, temperature of the wheels. If you've got a cold day, these things are going to be hard, and they're going to have a different traction than a warm day. So if you're practicing in your facility and it's really warm in there, and then you go to a competition and it's cool, it's going to turn different. Battery level. You need to do some tests. If you have time to work with your kids to make up a graph, and at certain battery levels, see when your robot is most consistent. And then, in other words, if you put a fresh charged battery in, right off the charger, it's going to spike over 9 volts. And it's going to make it just go like crazy. That thing's going to fly 100 miles an hour. But as it gets into it, it's going to start slowing down. There's a long period where it's around 8.5 volts for a long amount of time. So you can actually find where the best spot is, where you get to run all the missions on that best spot. Then it's going to reach a point where all of a sudden the battery charge drops, and it's not functioning again the way you originally thought. So you're out there, you're making it do something, and it does it great. You go to do it again, and it missed. You do it again, oh, now it doesn't. So there's a lot of inconsistencies, and it'll make you pull your hair out. But you got to work through them, keep track of your voltage level, keep track of the temperature in the room. Believe it or not, try to keep it around 70, which is most facilities. So if you have your own personal place that's warmer or colder, try to, when you're doing practices with the robot, try to keep it close to around 70 or so. I think that's what most of the government buildings are, and that's where Carmen Ainsworth is where we have our competition. That's probably what they have it at.
Sure. And one of the things that
I have a question. On the battery level, let's say the optimal is 8 volts.
Right.
So what do? You're going to discharge it to be 8 volts because you know that speed is that the optimal is there.
Right. What we do is, as soon as you get it off the charger, you hit the button and run it for a few minutes.
Okay, so
You can actually plug it into the computer, and you can see where the level is.
Yeah, but so you have to just charge it. Let's say if you have new batteries, then if you know the optimal is 8 volts.
Right.
Okay.
And you don't if your optimal is 8 volts, of course you don't take it down to 8
No,
volts.
yeah. a
You,
little
you
bit,
bring it
yeah.
down.
Maybe
Basically, our rule of thumb is
Uh-huh.
you charge it, you run the motor for a few seconds, and you're ready for the field.
Oh, all right.
You don't want to go out there with a fully charged battery because, you know, not consistently will it be that, you know. It's hard to zero it. I mean, there's so many differences, you know. But if you have a graph and you can kind of, you know, as it runs, keep an eye on the voltage, run it, and you'll get a feel for it, you know. And you can pretty much know where your best driving zone is. And of course, maximum voltage and minimum voltage is somewhere in between. And that middle area gets a pretty wide range. Enough to get you through a 2 to 3 minute run at the competition. To be consistent every time.
Okay,
Go ahead.
thanks.
I was going to mention about sensors, but the next the class that's going to be after this is going to be about sensors. But just to touch on it for a brief period, in the design of your robot, you will want to use some form of sensors to be able to react to the conditions on the field. One such device is one of these. Oh, someone took it. Is an ultrasonic sensor. One of the ways.
There's one right here.
One of the design ideas we had on this robot was at one point we were having many issues with being able to maneuver through this section of the playing field. And what it also forced us into doing was all these turns that were required down here had to be all different, depending on how this robot came out of the base. All right. Let's say if it was closer, well, we needed to turn it so much more, or so on and so forth.
Yeah, sometimes when it lurches off, takes off, sometimes it kick to the right a little bit, or it may go straight. And that little difference here can be a big difference down there. So, unfortunately, we didn't design our robot for this huge sensor. So, we ended up rearranging to get that darn thing in there, so when we come out here, we can check how far we are from the wall. If we're closer to the wall than original, then it'll turn a little bit more. If it's farther, it'll turn less.
And most of these kind of things that occur, you guys won't really need to worry about. But it's those kind of design goals that you have to sort of put in front of your robot. Maybe the field is crooked. Well, how are you going to deal with that? Maybe some piece is just off by a few millimeters. Will that throw your robot off?
It's good to design around that. Make sure that the item or the robot being off a little. So let's say you have a loop and you want to hit the loop with a rod. What are the odds of hitting that across the field? Well, if you rely on that one rod, most often you're going to miss. What can you do to compensate? Add 2 rods. If the one rod misses, then maybe the second won't get it. You know, find ways to multiply your ability. So if you don't make it the first time, some other means